going to take one more sidestep into history for just a second here and introduce you to Francois Arago. He was a French physicist about the same time as Ampere. In fact, he was a student of Biot. Uh, and he discovered something that was actually kind of puzzling to people at that time. Of course, a lot of people were trying to experiment with magnetism and electricity, but Arago discovered that if you took a compass and set it near a metal surface and set that compass vibrating back and forth, so oscillating and swirling around, it would damp out. It would slowly come to a stop. And that happened whether that surface was magnetic or not. So, for instance, copper or aluminum, things that don't have magnetism of their own, they aren't ferromagnetic anyway, like iron would be. And nonetheless, they brought these compass needles to a halt much more quickly than they would have otherwise. And this was actually kind of a mystery. In fact, it was one of the great mysteries of the early 1800s in electricity and magnetism, and it took Faraday to solve it. Let me show you an example of what Arago discovered here. I've got a compass, and I've got it sitting on a wooden block there, and I'm going to take a magnet, and when I swing that magnet, it's going to set that compass spinning in circles. So it spins around and around and around, and it keeps going because it's pretty loosely attached to a peg there. And it goes for 8 or 9 seconds at least spinning until it finally comes to a halt again. Now if I set this thing on top of an aluminum block instead, and once again do the same thing by flicking the magnet, you'll notice that it comes to a halt pretty quickly compared to before. It's about half as long that it spins. So it's not a dramatic effect, but it is a noticeable effect that this compass needle is damped out simply by being in the presence of a metal. And it was Faraday who figured this out for us. Because what he said is that if I have an induced current, that induced current creates its own magnetic field. So let's look at what happens here. Let's imagine I got a copper sheet, and I'm going to take a bar magnet instead of a magnet compass needle, and bring that bar magnet down to the surface. As it comes down to the surface, it's going to set up currents in that. It's going to induce currents just because of Faraday's law, and those currents are going to be set up in such a way that they'll spin around kind of in little loops in the piece of metal, even if it's not a wire. In other words, they'll form what are referred to as eddy currents, little circles of current. And they'll of course come to a stop once I bring my magnet to a halt. But then if I turn around and pull the magnet back away again, I get the opposite effect. The currents once again form, but now the field's the opposite direction. So either way I go, the field is actually being formed to repel the motion that I'm trying to exert. In other words, it's trying to damp the motion of this magnet with respect to the copper sheet. This is actually kind of interesting because what this means is these currents in there are set up simply because this thing is a conductor and because it can have induced currents in it, but those currents act as a drag force on the motion of the two objects. That drag force shows up as a little bit of heat generated in the conductor, but if I can somehow capture that, I can actually use it for a beneficial purpose. I can convert the motion back into electrical energy. And in fact, this is how regenerative braking systems in modern day hybrid automobiles works. The idea is that if I have brakes where I can take advantage of metal plates that can harvest the electricity by being put in the presence of a magnetic field, then I can drag the brake hubs to a stop and pull the electricity out to actually work to heat recharging a battery system in a car, where in a normal old-fashioned brake system all that happens is the friction causes it to stop, and friction generates heat that's totally lost, and in fact can do damage if you ride your brakes, for instance. Where in a regenerative system, when you tap on the brakes at normal speeds, all that really happens is it produces electricity that goes back into the batteries. Let me show you an example of this in action here. Of course, I don't really have a brake system in a car, but I've got something sort of interesting nonetheless. It's a pendulum here. So that's just a copper disc. It's kind of paper thin, but it's hanging from a metal dowel. And if I set that thing swinging back and forth, it's just a simple pendulum. So it just sits there and swings back and forth. Nothing tricky going on here. Now the interesting thing is going to happen if I take that metal disc, that copper disc, and put it in the presence of a magnetic field. So I've slipped into the situation here a little yoke of a magnet, and the disc is actually going to pass between the north and south poles of this magnet as it swings back and forth. And what you're going to notice here is the free swinging doesn't happen anymore. It comes right to a halt. Okay? And that's because of this effect that I'm talking about. It induces currents inside that metal disc, that copper disc, and those currents act to drag the force down to a stop pretty quickly in this case. Now, I can actually prevent this from happening by using a disc that's got slits cut in it. You'll notice this thing looks kind of like a fork or a spork or a spatula or something. And those little slits cut in it are going to prevent those eddy currents from forming quite as well. So what'll happen is this guy actually gets damped a little bit, but not quite as much, because now I don't have as big eddy currents to slow it down. So this is a very useful effect of Faraday's law in real action here, where the fields that are generated because of the induced currents can actually be used to drag something to a halt and used for braking.